Uh, Hold on, trouble. This not a complicated or part of the cursor and the formula. Oh my gosh. Let's go.
The second fundamental principle of cosmology. This comes, like so much of astronomy, from the study of spectra.
Spectrum. So if we remember, a spectrum is what happens when you spread the colors of light out into the colors of the rainbow, and we assign each color a wavelength, remembering blue light and ultraviolet has short wavelengths.
Blue light, red light, the burn, other hatchet.
Yellow, orange, red, infrared as you get the longer and longer wavelengths. And that's the wavelength of light that you're going to measure. You measure it in angstroms, which is 10 to the minus 10 meters per angstrom. So very, very short wavelengths.
What we plot is the amount of energy at each wavelength. So you can see these wavelengths have a lot of energy, and these wavelengths down there don't have very much energy coming out of that particular wavelength.
And so when you see a spectrum like this, it's actually a mixture of two things. Part of it is because we're looking at a galaxy in this case, full of stars, and the stars are hot, and hot things glow, just like if you really turn, for example, your stove top up really, really hot, it'll start glowing red. That's because it's hot. But then there are these little narrow lines, absorption lines, and sometimes there's emission lines. And that's due to the atomic transitions of each element. They have these places of energy motion between the electrons through different levels, and those show up in places of color. And so, for example, hydrogen has very specific lines. For example, at 65, 63 angstroms is one of the big lines of hydrogen, H alpha. But then things like sodium, magnesium, various molecules, calcium, all have different things.
Yeah. So this is very familiar to any astronomer. We would look at a spectrum like this and read off which elements are there. Now, that's all well and good. But the strange thing is, this is a key observation, is that when you look at a far away galaxy, you see a different spectrum from a nearby one. So here's a spectrum of a
the teacher what explained it to the visible spectrums and the portions of the electromagnetic spectrum that is visible to human eyes. Electromagnetic radiations are in the range of the wavelength. As a colored visible light offers simple light, or red or blue, and example in galaxies.
Nearby galaxy, and now let's look at a far away one.
So the red one is the distant one, okay.
And it looks the same, but shifted. Red shifted, moved to a longer wavelength. What you find is that every dip or peak or bump in the spectrum, every emission or absorption line, has had its wavelength increased by a constant ratio. And that ratio is called the redshift, and written for some unknown reason as Z rather than R, and it's given by the shift in wavelength divided by the wavelength you'd expect in a nearby galaxy or in your laboratory. So what's going on here?
Well, we know that waves get shifted by the Doppler shift. So we hear that in sound when a police car goes by you, the sound wave.
Example, energy pores uniting wavelength, and the colors red and orange.
Just get shifted, compressed, and stretched, and the pitch changes. Light's a wave, so that same effect's going to happen. So one could use the redshift to measure velocity. So when we see a redshift, it's like the objects are moving away from us. At the first order, that velocity can be calculated as the ratio of the shift of light is equal to the ratio to the speed of light.
Yes, this is an approximation of relative speed much less than the speed of light, but the galaxy is talking about it like that. So what it's telling you is if the light's been shifted by 1% longer wavelength, means whatever is produced has been moving away from us 1% of the speed of light. That's redshift of 0.01.
And so a galaxy that's been shifted by this much, though that's a big shift. So that means it's moving apparently at a good fraction of the speed of light. Now we're going to see that maybe it's not actual motion, but it's sort of,
yeah. So in fact, this is perfect.
The pitch changes. Light's a wave, so that same effect's going to happen. So one can use the redshift to measure velocity. So when we see a redshift, it's like the objects are moving away from us. In the first order, that velocity can be calculated as the ratio of the shift of light is equal to the ratio to the speed of light.
Yes, there's an approximation valid for speeds much less than the speed of light, but yeah, the galaxy we're talking about it like that. So what it's telling you is if the light's been shifted by 1% longer wavelength, means whatever is producing has been moving away from us at 1% of the speed of light. That's a redshift of 0.01.
And so a galaxy that's been shifted by this much, well, that's a big shift. So that means it's moving apparently at a good fraction of the speed of light. Now we're going to see that maybe it's not actual motion, but it's sort of apparently.
Yeah, and it turns out that almost every galaxy is moving away from us. There are one or two very nearby galaxies that aren't, but almost every galaxy is moving away from us. And if you plot how fast they're moving away from us against distance, you get this plot. What we're plotting here is how fast they're moving away from us. You see, that's 10,000 kilometers a second, 30,000 kilometers a second.
10% of the speed of light if it's a velocity.
Is this formula, this is spin calculations and the moving in the galaxies. This formula, velocity equal the constant in directions. For directions and galaxies, examples is the movie.
Yes, and then we measure distance, and we can see
It's a
there's
movie, right?
one-to-one
Of the galaxies.
correspondence. The further away you go, the faster the motion.
And this is known as the Hubble law, and it's parameterized as the velocity is proportional to a constant, Hubble's constant, which is about 70 kilometers per second per megaparsec, times the distance.
So 70 kilometers per second per megaparsec means if I'm a megaparsec away, I expect to be moving with the velocity of
This distancing and velocity, kilometers per second, huh? Or second.
70 kilometers per second.
Away from us.
Yes, so but away from us. Now, everything is moving away from us. This is something that Edwin Hubble discovered in 1929.
Is it
everything's
Laura
moving away from us.
Hubble?
That seems to violate the Copernican principle, e.g., we're no place special. It seems like we are a special place. We're this place that everything's going away from. We're a very unpopular place in the universe.
Yeah. Let's say you're living on some distant galaxy a billion light years away. Universe, as we've just said, may look uniform, but then they just tell, hey, everything's moving away from that point. That point must be the worst place in the universe, or something, but anyway, special. But it turns out that actually that's not quite the case. Show a little calculation here. Now, this is using vectors. If you're unfamiliar with vectors, we'll put a link for you to go and remind yourself about this a bit. But this is the vector form of the Hubble law equation. What it's telling us is us, we're announcing this galaxy. We've got two other galaxies. I call Galaxy A and Galaxy B over here. And what we said is the velocity is equal to a constant times distance. But these got a little arrow over the top, which means they're vectors, which means that the velocity is in the same direction as the distance and proportional to it.
Right, so vectors, remember, are how far and
velocity equal constant in
This
direction.
galaxy is relatively near, so it's got a relatively small velocity.
Is this
and the velocity is
volume?
in the same direction as the displacement vector. Right. This one's further away, so it's got a bigger velocity, and once again, it's in the same direction. That's writing down in mathematical form. Everything's moving away from us. The further away they are, the faster they're moving.
And so what you've stated here is Hubble's law, saying the direction and the distance is the same. So that all makes sense to me. It just says that direction we have one answer, that direction we have another answer. So it's just like we just saw.
Is this blue or red?
Now ask, okay, let's say you've got aliens living on this galaxy here. What would they see? Now, if they look back at us, we would appear to be moving away from them. Equal opposite speed. But how about this one over here? What would they see for this other galaxy over here? Okay. So, the first thing they can ask is, what's the distance, the vector displacement from galaxy A to galaxy B? So that's what's the vector from there to there? And that is simply xb minus xa, vector sum.
So that's the
vector. You go
arithmetic.
minus xa plus xb, and that gets you from there to there.
So that would be that arrow. Yes. Okay. So good.
So that's how far away galaxy B looks from galaxy A. And then we look at the velocity of galaxy B with respect to velocity A. And once again, the same thing applies. You've got a change in relative velocity is equal to velocity B minus velocity A. And so if you go back, it's got this velocity minus this velocity. It's going to tell how that thing appears to be moving from its point of view. Okay. So if you do that calculation, you know that relative velocity is velocity B vector minus velocity A. But we also know from the last slide that velocity B is h naught xb and velocity A is h naught xa. And so if you take the h naughts outside, it's just h naught times xe minus xa, just up here as delta x.
Ah, so it's the distance times the Hubble constant.
Yeah, so what they're seeing is the velocity of the aliens of galaxy A are seeing that the velocity of the galaxy B relative to them is just equal to the Hubble constant times the distance relative to them. That's what we see on Earth.
So that means what we've just shown using mathematics, we've literally proved, is that if we see this Hubble law, everyone sees exactly the same Hubble law. They see the same thing to us and to this other galaxy. We all see the same thing.
Yeah, so in fact, this is
This definitions and light is a one electromagnetic wave. The carriers energy across space. The energies per unit. Either unit time is indefinite or intensity, which does directly proportionalizations to square of the amplitude of electrical field on the light wave. This energy is not a continuum, but a reverse and discrete. United colored protons. Protons, what are the particles of light? It is teacher's explication.
consistent with a homogeneous uniform universe, the Comprimento principle, because not only do we see galaxies uniformly, but wherever you are, you see everything moving away. So how can you work out where the real
So no matter where you are.
I guess we're going to have to think about general relativity this, but it strikes me that if we think of the universe literally seems to be the further away, the faster the motion. So that means the universe is expanding. So let's do a balloon analogy. So let's just think of the universe as being the surface of a balloon. I'm going to put little dots on it. And as I blow the balloon up, every dot, which is a galaxy, is moving away from every other dot. So the galaxies are expanding away from each other. And the further away you are, the faster the motion will be as I blow the balloon up. So I sort of get Hubble's law. But where's the center? It's the center of the balloon. And what was that? That was when I started blowing the balloon up. So the center would be like the immortal equivalent to the Big Bang. When you started
Is the beginner.
Yeah, because we can't really tell what the center is, because you can never actually measure if you're moving, or you can measure if you're moving relative to something else.
Yeah.
Another analogy would be like baking a bread. Let's say you had a sultana loaf, you bake it in the oven, and we'll have sultanas as galaxies, the dough is transparent. As it gets bigger,
not from Australia, a sultana is a raisin. So it's raisin bread or
Raisin
sultana bread. Yes.
okay, so anyway, small black things inside your bread, doesn't really matter what they are. And as the bread gets bigger and bigger, it carries them all apart. So every sultana, every other sultana is moving away from us. Unless they actually look outside the loaf to the oven, they can't really tell which one's moving. Likewise, for your balloon, if they look outside their sheet of balloon, they can see where the center of the balloon is.
Yep.
We're talking about a three-dimensional universe, we can't see outside it. So here's my attempt to simulate this. So these tastefully colored spheres are
multiverse
galaxies, and they're all moving away from each other.
They're all moving away from us. They're getting smaller because they're getting further and further away. So we're literally embedded in this universe. And if we ask ourselves, well, where's the common center? The common center is right at the beginning of when we started, when we are all crammed into the same spot.
So from where we're sitting here, it looks like everything's moving away from us, but if we were actually on that dot or any dot, we would see exactly the same thing. So those are our two clues. We seem to have a universe that looks the same from any point of view, and it's one that's everything's moving away from every point.
Okay.